Good morning, good afternoon, good evening, wherever you may be in this great big world. Welcome to Windows Container Networking and Rancher 2.3. This is obviously the latest in our Master Class Series here from Rancher Labs. It's October 29th, 2019. We have two folks from Microsoft joining us today, Mike Kostersitz and Dinesh Govindasamy. One is Principal Program Manager from Microsoft, and Dinesh is a Principal Software Engineering Manager. I myself, I am Eamon Bauman. I am a field engineer from Rancher Labs. Rancher Master Class Series, we try and keep these master classes to about 40 to 45 minutes or so. Questions are always welcome. So if you have anything you want to know more about Rancher, know more about the topic at hand, anything like that, go ahead and fill out a question. You have the option to send it privately or send directly to us here within the GoToWebinar. So use that questions tab. We may respond to all of those questions. So like I said, if you want to mark that question as private, go ahead and do that, and then we can respond directly to you. This session is being recorded, so all of our online meetups, all of our master classes, anytime we're doing community engagement presentation is recorded. It's available on YouTube, so you can go to that URL at the bottom, youtube.com/C for channel and then Rancher. Everything is going to be tagged with hashtag Rancher K8S. We can also join the conversation on Slack. There is a Rancher user Slack. If you go to slack.rancher.io, it will redirect you to our Rancher user Slack. You can join that Slack. There's a bunch of different channels that you can ask questions about Rancher-specific concepts, Kubernetes, networking, containers, all that kind of stuff. There's also a masterclass channel where discussions about these master classes occur. Speaking of master classes, we have two upcoming ones. On November 5th, so that's looking like next week, we'll have Dan Akristini as a DevOps engineer who's going to tell us about Kubernetes the fun way, bootstrap a full-featured portable K3S cluster. And then the week after that, another masterclass with a couple of gentlemen from Portworx, the topic being data security strategies for Kubernetes. You can view all of these upcoming classes, and I believe historical ones, at rancher.com/Kubernetes Masterclass. So with that, I will go ahead and turn it over to our friends from Microsoft here. Let me go ahead and stop sharing my screen, change up that presenter. All right, Dinesh, you should have control. Take it away.
Mike?
Yeah, thank you very much for having us. My name is Mike Kostersitz. I'm a program manager at the core networking team at Microsoft, and I own the ecosystem around container networking, as well as bringing new functionality to Windows Container Networking that are maybe available in Linux or maybe are not available in Linux. Dinesh, why don't you introduce yourself?
Hello, everyone. My name is Dinesh Govindasamy. I'm a dev manager in Core OS Windows Networking Group, working for Microsoft, and I lead the charter for Windows Container Networking. Thanks, Mike.
Okay. Can you skip forward?
I can. I thought I did. Can you see it?
Yep. So I want to talk about a little bit about Windows Server containers. Before I hand it off to Dinesh about the that goes into the technical stuff, I'll talk about what's new in Windows Server containers, the prerequisites to get started with containers on Windows Server. And then Dinesh will take us through the Windows container architecture, the networking introduction, and also how to debug container networking in Windows, because that's slightly different from Linux. We'll talk a little bit about resources available to in the public, and then also we'll leave some time at the end to answer questions in the questions tab, and close it out after that. Thank you very much. So Windows Server containers have been around for a little while. They have become stable in Kubernetes 1.14 earlier this year. We have made continuous improvements all the way to the latest version 1.16, where we introduced kubeadm support for Windows Server. We also introduced VM isolated containers, which gives you an additional layer of isolation over process isolated containers. The Windows subsystem for Linux, WSL2, is now running in a container on your client or server. Improved network performance with the introduction of direct server return functionality in our load balancers. We also support multiple subnets per node now, and we're looking at bringing Linux containers on Windows so that you can run all your workloads on the same Windows server instead of having to run multiple different operating systems as your host. And of course, we're working on many more functionality, about things that I'm not able to talk about today. So to get started, you need Windows Server 2019 Server Core or Data Center Edition. Keep in mind that there is licensing differences between Server Core and Data Center. Server Core allows you to run 2 virtual machines and unlimited process isolated containers. And Data Center Edition allows you to run unlimited virtual machines and unlimited process isolated containers. You need to have Docker installed. Here's a couple of command lines to get that, and there's more in the documentation outlined in the resources section of the deck. You need to install the Docker provider, then Docker itself, then enable the Windows Container feature, restart the computer, basically deploy 2 Linux nodes, one for the Rancher host and then 1 Kubernetes worker. And then just run the Rancher web server on the Linux node with a simple Docker run command and go to the web UI and deploy your first cluster. If you want more information, check out the docs at rancher.com. In the quick start guide there, it guides you through all the steps to setting up your Windows node and also your Linux nodes. With that, I'll hand off to Dinesh to take us through the architecture, Windows networking, and debugging.
Thanks a lot, Mike. So in this section of the presentation, we're going to go over the high-level architecture for Windows containers. And I'll also talk about the building blocks of Windows container networking and how it compares with Linux. We'll also go through the Kubernetes network connectivity and how it's been implemented for Windows, and a demo of Rancher Kubernetes cluster with Windows applications. And then we'll also have a small debugging session to debug how to debug a Windows container networking failure. So Windows container architecture. So there are 2 main inbox services, the host compute service and the host network service in the operating system, that provide the required Windows container functionality. The host compute service is responsible for the lifecycle management of the job objects, that is like the containers, whether it's a Windows container or an Hyper-V container. And the host network service is responsible for providing the networking for both Windows containers and the Hyper-V containers. There is a thin layer called HCS shim, which is a Go interface for both of these services. And the Docker D daemon, Container D daemon, kubelet, kubeproxy, or any other daemon basically will program these 2 services through HCS shim. Now, let's take a look at the container networking basics and how it's been implemented with Windows. The first one is the network namespace. In Windows, the network namespace are implemented using TCP/IP compartments. Conceptually, the TCP/IP compartments are a logical container in the TCP/IP stack. So the network layer in the TCP/IP is responsible for making sure that each TCP/IP compartment is isolated and forwarding traffic between the compartments is prevented. All IP related objects such as IP interfaces, routes, and everything reside inside that unique to that compartment. In Linux, the layer 2 functionality is provided by the bridge and the IP routing. In Windows, the vSwitch provides the layer 2 and layer 3 switching functionality. You can, if you're familiar with Open vSwitch, this vSwitch is analogous to it. And you can have as many instances of vSwitch. You can also dynamically add and remove switch ports to this vSwitch. And vSwitch has its own forwarding plane and forwards packets based on MAC address and the VLAN tagging. The IP links. In Windows, the container interface is implemented using the virtual NIC, a combination of virtual NIC and the vSwitch/VFP ports. A virtual NIC, which can be a host vNIC or a VM NIC. In case of Windows containers, we use the host vNICs. In case of Hyper-V containers, we use VM NICs. They are added to the network namespace and then bound to the corresponding switch port in the vSwitch. In Linux, the IPVS and IP table rules provide the rich packet filtering functionality. In Windows, a combination of firewall rules and VFP rules provide the similar packet switching, packet filtering functionality. VFP stands for Virtual Filtering Platform. It basically provides, it's a match action based packet filtering policy engine. And I have a separate slide to go in depth on VFP. So now let's put all of this building blocks together and look at how bare metal networking works in Windows, and then overlay container networking on top of that. So you have a host here, and you have a physical NIC connected to the host. By default, that physical NIC is basically exposed in the root namespace, and the applications running in the root namespace will be able to use this Ethernet NIC. Now, when we add a virtual network, which is basically a container network, to this host, it's a virtual network is a construct in HNS, which comprises of creating the vSwitch on the host and also setting up the required host settings in order to enable you to do containers. So we create a vSwitch on the host. The vSwitch binds to the physical NIC. A new virtual NIC is added to for the host partition and basically exposed to the host partition. So the MAC address and the IP address that was on the physical NIC is now moved to this virtual NIC. Now the applications that are running on this host namespace will be able to use this NIC to talk to the outside world. Now any switch ports or any NIC that is connected to this vSwitch will be able to either talk to the host partition or to the external world based on the policies. A container namespace is basically creating a network namespace on the host, in this case a TCP/IP network compartment. A container endpoint is creating another host vNIC or a VM NIC for specific to that container, and then connect it to the network namespace and also bind it to the corresponding switch port in the vSwitch. The container by itself will have its own IP and the MAC. Now the NATing or the load balancer functionality is provided by the VFP. VFP is added as a switch extension to this vSwitch, and there are rules and layers that basically help us to achieve different kinds of traffic, whether it is pod to pod, pod to internet, or pod to service web. Now let's take a look at VFP. VFP is added as a switch extension to the vSwitch. So any traffic that is seen by the switch will also be seen by VFP. Now VFP is port specific. So every port has its set of instance of VFP rules and layers. So VFP has different layers. The layers can be metering, ACLing, VNet, or SLB, or much more. Inside each layer, there are different groups, and the groups can be whether it's IPv4 or IPv6, whether it's in direction or out direction or user defined. Inside each group, you have rules. Remember I said that VFP is a match action based filtering engine where you can specify a match condition. Match condition can be anything from protocol, source IP, destination IP, source port, destination port. So that particular packet will be filtered here based on the condition provided. And then you can apply an action on that packet. The action can be SNAT, source NAT, or destination NAT, or LB NAT, or NCAP, DCAP, or lots of data plane primitives are there. So these set of rules are basically applied to the packets that are flowing into that NIC, both on inbound direction, and also on the outbound direction. Now VFP provides the data plane and HNS provides you the control plane. Together we basically form the different kinds of network connectivity for Kubernetes. Let me dig a little bit deeper on how Rancher is using Kubernetes for Windows in their deployments. So on the left side, you have a Linux worker node. On the right side, you have a Windows worker node. So this is like kubelet, the CRIs, and then the CNIs, and then the kuproxy, and then the CSIs. So Rancher uses a specific type of network type called overlay-based networking, where we use the VXLAN technology. So the containers are going to be in a CA space, which we call customer address space. And the overlays, the provider space is going to be the physical physical network connectivity. Each container host is allocated a specific CA subnet. It could be both Linux and Windows. They will have their own subnets, and they will have their own distributed MAC address specified for each host. Flannel, which acts as a network controller, is responsible for propagating this subnet and the MAC address and the provider address to every other node in the cluster deployment. So Flannel D acts as the network controller. So when a Windows worker node is trying to communicate to a Linux node, and if the destination falls within that subnet, it basically uses the distributed router MAC address as the destination MAC and sends the packet out. And then that particular host takes care of delivering it to that specific pod. The same thing when Linux sends it to Windows, Windows ensures that it gets delivered to the specific pod. Now let's go look at the Kubernetes network connectivity and how it's been implemented for Windows. I'm going to reuse the same diagram, so let me spend a minute explaining this diagram. So you basically have a host, and you have a vSwitch, and you have the host namespace here. This is the host VNIC, the MAC, and the IP, and this is your physical Ethernet NIC. And then you have two pods in this host. They have their own IP and MAC. They are from CA space. Basically, they are on the overlay networking, and the underlay is this 192.168.0.5 space. Now, the first one is pod-to-pod connectivity. So pod 1 is trying to send the traffic to pod 2. So the packet reaches the port 3. So on each port, we have a similar set of VFP rules, and they are programmed by HNS. So assume there is no ACL. The packet reaches the encap layer. So based on Flannel propagating that information, we have programmed a encap rule that says that if the destination falls in one of those spots CIDR range, encap the packet with the provider address as the host IP. So you can see that this is the inner packet, and the outer packet is added. Outer packet header is basically the 0.5 sending to 0.5 because the destination pod is also in the same host. We also fix up the inner MAC. The inner MAC of the packet, basically the 80s MAC has been fixed in the inner packet. Now the same packet reaches the forwarding plane. VFP has this feature where in addition to forwarding packets based on the outer header, it also is able to forward packets based on the inner header. So it looks up the inner MAC, figures out the inner destination is part of the same host, and it forwards the packet to the port 4. Once it reaches port 4, the packet, again, the set of VFP rules are executed. There is a specific rule on the inbound direction where we decap the packet. Basically, the outer header is removed, and then it is given to the TCP/IP stack inside the pod 2. And then the TCP/IP stack forwards the packet to the endpoint that is listening for this packet. So this is how pod-to-pod connectivity works for Kubernetes in Windows. And I just want to highlight two things. The Kubernetes requirement states that pod-to-pod connectivity should not be NATed and should provide basic L3 connectivity across them. And this is why we didn't NAT any traffic when pod 1 is trying to talk to pod 2. Now let's take a look at the outbound NAT connectivity for Windows. A pod 1 is trying to reach internet. So by default, the way VFP rules are programmed in Windows is any traffic leaving the pod 1 or pods will be NATed. But there is also an exception class in that layer where it says that if the destination falls in either in the pod CIDR or in the service CIDR, don't NAT it. So that's why pod to pod doesn't get NATed. So here pod 1 is trying to reach internet. The packet reaches the port 3. Since this is a IP address the destination IP doesn't fall in the pod CIDR or in the service CIDR, it basically bypasses the encap layer and it goes to the NAT layer. VFP has this rule called SNAT, which creates a stateful NAT where it replaces the source IP of the pod with the source IP of the host and the port and sends the traffic out. The reason why this is a stateful NAT is so that a flow is created, so that when the response comes back, it again will be mapped back to the pod 1. Now let's take a look at pod to service web. I'm assuming everybody is familiar with service web. So basically you have a cluster service web defined for this cluster, so which is again another specific space. So we have implemented a load balancer functionality, which we call the MUX, in our the host management host VNIC. So what we do is we basically we have two different types of implementation. One is called non-DSR and the other one is called DSR. But in this non-DSR case, the packet will be routed from the pod to the MUX, the management NIC, and then it will be there will be a LB-NAT rule that will apply basically and select a specific DIP. So in this case, there is an LB programmed in the VFP that says that if the destination is this web, select one of these DIPs. We currently have the selection algorithm is based on the phi tuple. So the source IP, destination IP, source port, destination port, and the protocol. We hash it, and based on that, we select a DIP. Now let's take a look at the packet flow. So the packet, the pod 1 is trying to reach a service web 10.43.0.10:53. The packet reaches port 3. Now, since the destination is a service web, there is a custom route rule that says that encap the packet and send it to management NIC. So you can see that the inner packet is encapped with an outer header. So this is like a within a host encap where it will not go out. So basically the packet reaches the management NIC. Once it reaches the management NIC, the packet will be hat-pinned and an LB-NAT rule will be applied. The LB-NAT rule is basically selecting a specific DIP. So here we have selected the 80 and we also have fixed up the MAC for that pod 80. Now, once the packet, we also encap the packet because this is an overlay networking. So we encap the packet based on the destination MAC and the IP that it was selected. The corresponding provider address will be programmed in the outer header. Since this destination pod is also in the same host, we basically use the same host IP as the source and destination. Again, VFP does the inner MAC forwarding and forwards it to the port 4. Again, the inbound rule, decap rule kicks in, it decaps the packet, and then it delivers the packet to pod. So this is how pod to service web connectivity works in Windows. I covered a lot of data, and I'm assuming we'll cover the questions at the end, right, Mike?
Yes, Dinesh.
Okay, so let me go over to a demo and show the same Kubernetes network connectivity and how it works using Rancher. So here is a Rancher deployment that Mike helped me deploy in our on-prem environment. So you have a Rancher demo app created. So you can see that there are So I wanted to show the nodes. I'm assuming there's a way to go to nodes. Sorry,
If you click on the name of the sandbox cluster, so go to the back to that and then click sandbox. Yep.
Yes.
And then you can click nodes.
Sorry. Okay, no so problem. You can see that this is a cluster where you have two Linux nodes, one as the master and one as the Linux worker, and then there are two Windows nodes added as the worker nodes. And you can see the corresponding provider address for each of these nodes. Now let me go ahead and click on a Rancher demo project that was deployed. So you have a WinWeb server application that is deployed in this cluster, and it has 3 pods currently running. 2 of them are running in this host, and 1 of them is running in this host. The cool feature of Rancher is you can basically remote into the pod directly from their UI. So this is a pod that is having a CA space of 42.1.92, and this one has a space of .3.34. So these are two different. You can see that they are allocated in different CA subnet across different nodes. Right? So let's go ahead and curl this particular. I have a WinWeb server running on port 80. And you can see that I can curl this WinWeb server, and the current IP of the node is displayed on this web server. Now let me go ahead and curl the pod to pod. So I'm curling 42.3.34. So you can see the 42.2.3. So this is basically pod to pod across different hosts. Now let me go ahead and get the service web for this application. And so you can see the service web allocated for this application is this. So the service header is 10.43. So let me go ahead and curl 10.40. So this is basically the service web for this application. So you can, since the service, there are 3 pods on the backend dip. So you basically get load balanced for every connection across these 3 different pods. So you can see that I hit 42.1992, 1.93, and then 3.34. So the backend dip is load balanced across these different pods. Now there is also a node port programmed on these applications. So the 32.32598 is the node port that is programmed. So let me go ahead and get the server IP. So this is the host IP of each of these nodes. So the same thing, the node port gets load balanced. You can see that it called 3.34 in the first request. In the second request, it called the 1.92 and then 1.93. Now I showed pod to pod. Actually, I didn't show pod to internet. So let me also do pod to internet. So you can see that I'm able to, this is basically pod to internet connectivity. And then I also showed pod to service and pod to node port. Now let me also show Windows to Linux connectivity. So we also have a Linux app, Nginx app deployed on the Linux worker nodes. So there is another Linux worker node that's sitting on the same cluster. Look at the IP subnet for the Linux is 0.0/24. So I'm from Windows node, I'm hitting a Linux pod, which is on the 42.0, and you can see that the web page is getting opened. And I can also hit the service web for the Nginx app. So if you go to service discovery, you can get the Nginx app cluster IP, so which is this high IP. So you can hit this as well. So I showed pod to pod, pod to internet, pod to service, pod to node port, and pod Windows node, Windows pod trying to reach Linux pod, and Windows pod trying to reach the Linux service. Now let me go ahead and walk through how networking is done. Debugging is done in a Windows container networking. When you face an issue with Windows container networking, let's see how to debug it. So basically, you have kind of a similar flow for debugging any kind of networking failure in a cluster. So you look at the spec, you make sure that the kubelet and kubeproxy logs looks good and it has deployed the pod. Look at the CNI spec and the CNI logs based on whichever CNI you're using. In this case, you'll be using the Rancher CNI and the WinOverlay CNI. So you make sure that the container has a specific endpoint added and the IP and the MAC address of the container looks good. Now, as I said, the HNS provides the control plane. So once the CNI is programmed correctly, look at HNS state. I'll walk through the collect log script and how to collect that in a active environment. Look at the network, the endpoint, and the VFP. Make sure all the expected policies are programmed in those. Once HNS state looks good, then look at the VFP output and look at the VFP state and make sure that the similar to IP table rules, VFP rules also programmed correctly. If all of the control plane state looks good, then collect the packet capture and then look into the packet capture and see why the packet was dropped. Now, in this demo, what I'm planning to do is I have a host and I have another host. One pod is curling another pod. In the demo I'm going to show is the same host, but the slide I have is across host. Sorry about that. But basically what I did is I stopped the website in the other pod. So the host one, the pod is curling the destination pod. The packet reaches the container port. No, since this is pod to pod, there should not be NAT and it should be basically encapped. So the packet gets encapped and it gets forwarded to the forwarding plane, and the forwarding plane looks at the destination MAC and forwards the packet to the corresponding port. Now on the inbound direction of that port, we will decap the packet and then the packet will be given to TCP/IP stack. Since the TCP/IP stack doesn't have a listener, since I stopped it, it will be dropped. Now let me go to a machine. So this is the same Rancher machine. This is one of the Windows host. So in the next few slides, we will tell you where to get this specific script called collect logs. So you run this collect logs on that node. So it generates a folder, and inside that folder, you have pretty much every networking related files that is collected as set of logs in this node. So for example, in this case, it generated this. So there is a file called network.txt. So this file shows on the container host what kind of network is created. So as I said earlier, for Rancher network architecture, we are creating a VXLAN overlay based network. And you can see the JSON output of that network. So as I said earlier, this particular overlay networking has a specific type of policy called host route, where you basically have every other node's destination prefix and their MAC address and their vSIT and the PA space for that. So this is very important if you expect two pods on two different hosts to talk to each other. So this is what we use as the inner destination MAC and while we are encapping the packet. So we have 4 nodes in this cluster. For this node, you have the 3 other nodes remote subnet policy. And this is programmed by Flannel. So if some of the policies are missing in this, make sure that Flannel is working properly and Flannel is able to program these policies to every other node. For this node, you can see the address prefix allocated here. So in this node, the 1.0 is the address prefix allocated, and the vSIT allocated is for this node. Now there is another file called endpoint.txt, which basically shows the list of container endpoints we have on this host. So you can see that these are the list of endpoints. Not all of them are there in the current host because some of them are remote endpoints. A remote endpoint is a concept where that endpoint is not actively present in the local node, but it is present in some other peer node. So you have basically one of these endpoints. I'm going to look at the policies programmed on this endpoint. As I said earlier, every container created in Kubernetes Windows by default will have outbound NAT programmed. But we do have an exception list where we say that if the destination falls in one of these space, which is the pod seeder and the service seeder, don't NAT it. So that is this policy. Make sure that this policy is programmed. We also have a CA route policy where it says that if the destination falls in the service seeder, make sure you encap it and send it to the mux. And then we have the PA policy for the overlay networking. So this shows the list of policies programmed in every container endpoint. So you also have some of the ACL policies by default program, but you can also program your own ACLs. Now this shows the control path state of the HNS. Now if you look at the VFP output.txt, you can see that the data path output. So you can see, let me take one of the examples. So this is a pod that I just used. So you can see the policies for this pod. So in the beginning, you have the mapping policies. For now, let's ignore it. Then you have the starting layer, which is the ACL layer. And then you have the in and then the corresponding out. In this case, we are not programming any ACL, so it's gonna walk through. Then you have the encap layer, which is basically encaps the packet. And this is where we have that remote subnet rule, whatever we programmed on the endpoint on the network, where if the destination falls in one of this, make sure you encap the packet with the IP of this and with the MAC address of this. Right? So this is basically the remote subnet MAC address that we programmed with the vSID key. So similarly, we have the NAT layer after this, which will say that you can program the NATing. So these are the exceptions for that outbound NAT. And this is the TCP NAT and the UDP NAT. So I think once you go through this set of files, you should be able to familiarize yourself the set of rules we are programming to achieve the specific type of connectivity. Now, let me walk through how to collect packet capture. So you go to this folder called debug. There is a start packet capture.cmd. So you basically start that, which will create a session using which you can basically capture the packets. So you go to the repro and repro the connectivity. Then you come back to the system and basically issue stop packet capture. So this will create a server.etl file, and you can use that server.etl file to basically look at the packet. So there is a tool called Message Analyzer, which is basically a free tool that is available to download. So you open that server.etl. Sorry, I opened the wrong file. So you open that server.etl in the message analyzer. So this is something that I collected earlier. Now I'm gonna look at the, sorry, it's gonna take a couple of seconds to load. So using this message analyzer, you should be able to apply different kinds of filters, whether it's TCP.port or the IP, and you should be able to look at the different packet capture at different layers of the stack. So you can see the entire packet capture is loaded. Now let me apply the rule, because since I curl to the port 80, so I'm going to put a filter on port 80 to see all the packets that were hit for this port 80. Couple of seconds. So you can see that these are different packet captures at different layers of the stack. And since the endpoint was closed, you can see that it is the connection is being tried at 243 and 244. Now let me take a look at the packet flow. So I'm going to remove the filter. So you can see that. So these are different packet capture at the origin. So the packet reached the port 14. So you can see the port 14 here. And you can see that the packet is getting encapped. So you can read this text where it says that the packet is encapped. And you can see that the packet, once it is encapped, it's successfully forwarded from port 14 to 15 because it's in the same host. Now you can also take a look at the packet here. So you can see that this is the outer header. So you have the host IP, and this is the VXLAN vSID, and this is the inner packet. So the 79 pod is trying to reach port 80. Now on the port 15, the packet reaches on the inbound direction. It gets decapped. So you can see the packet getting decapped here. and it also basically reaches the TCP/IP stack. You can see that the packet is reaching the TCP/IP stack, and you can look at the inner packet here, 79 going to 80. And after that, basically the packet is dropped because the endpoint is not there. So this is how you basically debug any networking failure in Windows. So just understand what the scenario should be, how the rules should be programmed, look at the kubelet side of things, look at HNS, look at VFP, make sure the policies are programmed right, and then take a packet capture and look at why the packet is dropped. Hopefully at that point, you'll be able to understand whether it's the policy programming is wrong or something is going on. I think that's pretty much I had. Mike?
Yes, thank you very much, Dinesh. This was a very good overview and insight into how Windows Container Networking works. As a quick summary, we talked a little bit about what Windows Server containers and what we've been up to since we released when stable in Kubernetes 1.14. You've seen that it's fairly straightforward and simple to bring up a Windows cluster and Linux workers in the same cluster if you desire to do so. You've also seen that Windows Container Networking is slightly different from Linux networking and requires a slightly different tool set to actually debug and investigate issues. The Rancher cluster uses overlay networking with VXLAN, and we also have ready-to-use debugging tools and resources that are available on GitHub and in the official documentation. If you switch me to the next slide, we do have additional resources available. One very valuable resource is the Windows Core Networking blog at aka.ms/networking blog. The Windows Container documentation, the Kubernetes Windows documentation, and then also the last link is where you can find the debugging tools for container networking and our SDN. This is the collect log script, the network tracing script, and then the other tools are linked there too that Dinesh just showed in the debugging session. With that, we're at the end. I hope I also was able to answer most of the questions that came up in the questions tab. And I will stick around for a little longer to answer the last few questions that are in there. And after that, I want to thank you all very much for joining us, and I hope we provided a good insight.
Yeah, Mike, Dinesh, thank you both very much for joining us. This was incredibly informative. Coming into this, did not know a ton about Windows networking and how there was interaction, especially with the vSwitch and the VFP. So it was very educational for this. So I really appreciate you guys doing this presentation. And there has been a ton of questions, and actually more are flowing in right now. So that's always a good sign that folks are invested and engaged in this topic. All right, so with that, we'll answer the last couple of questions. I will go ahead and stop the presentation at this point. And then if anyone has any follow-up questions, feel free to join us, like I said at the beginning of the presentation, in our Rancher user Slack. That is slack.rancher.io. There is a channel in there for our master classes. That's hashtag or # masterclass. We have 2 coming up next week on the 5th, and then the week after on the 12th. So thank you both once again very much for joining us. This is recorded. It will be up on YouTube. I would say probably in the next day or so, you'll be able to check it out on our YouTube channel, youtube.com/c/rancher. Thanks again very much for joining us.
Thanks a lot.
Thank you.